Where does the chain rule come from? I feel like this is one of those rules that easily becomes second nature without the need to understand what is happening at a deeper level. A reminder for those of you who are unfamiliar with this rule, or perhaps out of practice. This is the rule for when you have a function that can be split into two nested, more easily differentiable functions in order to differentiate the whole. The rule states that the derivative of these two functions, multiplied together, makes the derivative of the original function. The objective of this video is to explore why this is the case. While this is not strictly required knowledge, I would say that understanding the underlying concept is useful in and of itself, as an exercise in understanding calculus on a deeper level. Or, if you are like me, it is fun to fantasize about whether you yourself could have come up with such a rule. The first person to formalize this rule was Leibniz in 1676, although Newton was making similar calculations about a decade earlier. I want to first take a moment to build your intuition by using a helpful analogy. Imagine we have three gears, A, B, and C. If a full turn of gear A turns gear B twice, and a full turn of gear B turns gear C 3 times, this would therefore mean that a single turn of gear A spins gear C 6 times around. Because a full turn of A spins B twice, and each of those spins spins C 3 times, 2 multiplied by 3. This is the basic intuition. But to look at it in a slightly more mathematical way, let us imagine a function, y equals 3x plus 1 all to the power of 5. We could expand this and use the power rule term by term, but the chain rule is far quicker. To use the gear analogy, think of everything being driven by a fundamental gear, which here is x. X will always spin at a constant rate, and one full spin is 1 unit. For the sake of this explanation, let's class a full spin of x as representing an infinitesimal, essentially a tiny, tiny change in x. Whatever the base variable or parameter is, that cog turns everything else. So the x cog is turning the y function, y equals 3x plus 1 all to the power of 5. Now with our current setup, it is a little challenging to decipher how the x cog affects the rate of the function cog. So, the chain rule allows us to drop in a middle gear to simplify the rate finding. In this case, we can set the middle cog to 3x plus 1 and name it u, so u depends solely on the first cog. This automatically then makes y depend on the middle cog, y equals u to the power of 5. With two cogs in the chain, we can measure rates one link at a time. For the first link, if the x cog spins once, the u cog spins 3 times because of the scaling by 3. So what this is essentially saying is that for an infinitesimal change in x, the change in u will be 3 times larger. Essentially, for a single spin of the x gear, the u gear spins 3 times. In derivatives, we represent this as du dx equals 3. Notice that the derivative of the function is essentially a mathematically appropriate way to calculate the instantaneous scaling of the spin rate with respect to the gear before it. For the next link, from u to y, at any given moment, the rate at which this gear is spinning depends on the instantaneous value of u. Since y equals u to the power of 5, taking the derivative with respect to u gives dy du equals 5 times u to the power of 4. This is the exact number of spins that this gear will spin with respect to one full spin of the u gear. For those of you wondering what it means to scale something by 5u to the power of 4, if we were at u equals 1, the scale factor would be 5 times 1 to the power of 4, which is just 5. That would mean that at that instantaneous moment, a single spin of u would spin this gear 5 times, and so forth. But remember, dy du describes y's rate for a single spin of the u cog. What we really want is dy dx, y's rate for a single spin of the x cog. And for every one spin of x, u spins 3 times. So we have to multiply our dy du by the 3 in order to take into account the fact that it's spinning 3 times rather than just 1. And that logic is exactly why we multiply the rates of these functions, just like the gears in the initial intuition building phase of this explanation. So dy dx equals dy du multiplied by du dx. Substitute the two pieces. Dy dx equals 5u to the power of 4 multiplied by 3, which is 15 multiplied by 3x plus 1 to the power of 4. And there you have it. That final multiplication isn't an arbitrary rule we just have to memorize. It is simply the mechanical consequence of connecting these gears. When you see that dot representing multiplication in the chain rule formula, I want you to visualize that middle gear, transmitting the spin rate from the input x all the way to the output y. It is just the cumulative effect of rates acting upon rates. However, while analogies are excellent for building intuition, they are distinct from mathematical proof. For those of you who are satisfied with the intuition, you now have a solid mental model to carry forward. But if you are more interested in exploring why the gear analogy works from a strictly mathematical standpoint, and you want to see the rigor behind the intuition, then Brilliant has a really great exercise you can go through. It is a great interactive activity that walks you through the geometry of the gears, using the radius and velocity to prove that these ratios really do multiply together exactly as the chain rule predicts. It is a really satisfying way to close the loop on this concept, and as you can see, is a perfect extension to what we covered in this video. Anyway, I hope this video helps build more of an intuition on how the chain rule is actually working, and if there are any questions, then I'll be active in the comments to answer any questions.